Now that we know the basic structure of a neural network, we will dig into some of the details of how these modeling tools work. We will start with the concept of gradient descent. Recall that in our regression methods, we use calculus to find the minimum value of the mean squared error to determine the optimal value of the parameter estimates for the slope and intercept of our line. Instead of finding these values directly, we will use a method of calculus that instead uses a bit of guess and check. If we're at a certain location on a graph and we plug in new parameter estimates, will that make our error go up or down? If it will decrease the error, then we will follow that direction until we are no longer minimizing our error. If we consider a two-dimensional plot that compares some loss function on the y-axis to just one of our parameter values on the x-axis, you can gain an understanding of what it is we're trying to get at. Note that when we create a neural network, a random value for the parameter space will be initialized. Thus, a random point on our graph will serve as a guess to the parameter we should use and the error that this will produce. At the current location for the point, if we were to increase the parameter's value, we would decrease the amount of error. When training a neural network, hyperparameters, called the learning rate and momentum, can be tweaked to help our model training process settle in on an optimal set of values for the parameter space. By changing our learning rate or momentum, this will determine how much change in our parameter space for the weight values occurs between subsequent calculations of the error, to then determine how we're doing in the gradient descent process. As you can see from the animation, a small change in our weight value seems like it will get us to the minimum value for the error that we're looking for in this process. Notice, though, that it seems like it's going to take a long time for us to get to that point. Another thing we need to be mindful of as we're doing this is that we intended for our modeling process to find the lowest possible error, or what we call the global minimum of the graph. However, if our change in the parameter space for the weights is too small, it's quite possible that we will end up getting stuck in a local minimum. Remember, too, that our starting point in parameter space is randomly selected. So while this won't happen every time we run the model, it is a potential problem for us to consider. Increasing our change in the weights in the gradient descent process can help with this, or setting a different seed before running our neural network. Both of these things can take a bit of guesswork, though. With these things in mind, you might think then that using a larger learning rate would be the better way to go. However, if the learning rate is too big, we may never be able to settle on a minimum value of the graph at all. This means that we need to find a learning rate that is just right for the data we're using. Fortunately, the Keras package in TensorFlow, which we will be using to create our neural networks, has a predefined set of optimizers and what they consider to be good learning rates and momentums for the loss functions that we will be trying to minimize. We will take advantage of these as we start to build our neural networks. Finally, you should keep in mind that the graph that you see on the screen is a toy example of what we will really be doing. Remember, we're going to have hundreds, if not thousands, of weights and biases in our modeling process. Each of these will have its own dimension on the graph. We need to find the optimal combination of those values that will minimize the loss function that we use in our modeling process. While we won't go through all of the calculus that's required to determine next steps in a gradient descent, we will take a look at our XOR example to get a sense as to how something called backpropagation, a key process in training a neural network, works. Backpropagation is an algorithm for determining how a single training observation in our data set would like to shift the weights and biases to make the prediction for that observation a better fit to the actual value. Recall that randomly selected weights will be used to start our neural network process. Suppose that the equations that you see on the screen represent the randomly selected weights and biases, along with any transformations we wish to apply to our variables along the way. We take the input values for x1 and x2 and run them through the different equations to get a final output from our first iteration of training. We can see that all of the values are negative. Comparing these output values to the real value we were anticipating to see, and then squaring the difference in that error, we get the cost component for each of the input observations or rows of the table. Next, the backprop algorithm looks at each row of our data set and compares these output values to the real value to see if we predicted too high or too low. In each case of our first iteration, our predictions were too low. How can this be improved? Looking at the equation we used to find the final output, we can see that if the weights on either H1 or H2 or the bias term were bigger, meaning smaller negatives or larger positives, then our output would increase. This assumes that the values on H1 and H2 stay the same, or at least do not change sign. But something else could happen here. If H1 were to decrease, or H2 were to increase, we could also increase the value of our output. What this means then is that we need to consider the ways that the weights and biases of the previous layer of our model could affect the values of H1 and H2, just like we did for the final output layer, and potentially change those parameters as well. This is where the term backpropagation comes in. We move backwards through the layers to see how the hidden layers could change to affect the final output layer, and what needs to happen to the weights and biases from those previous layers to make these changes happen. If we had multiple layers, we would have to keep going back through all of them to update all of the weights and biases in an attempt to increase the final output value in this example. Remember, though, that this process happens for each row in the data set. Here, all of our rows happen to agree on what needs to happen to the weights and biases at each step, but that likely won't be the case in practice, especially when you have thousands of rows in your data set. Because of that, a weighted sum of the changes that each row desires takes place to determine the new parameter space in the next training iteration of a neural network. A final thing to note about this example is that the cost function value is much higher for the second and third rows compared to the first and fourth rows. Because these output values are much further away from the real values, they will be weighed heavier in the sum to help bring their predictions closer to the real values and reduce their impact on the cost function. Taking the advice of the gradient descent process, a second iteration through this neural network might take on the following form. Notice that the sum of our cost function elements has gone down. We're one step closer to optimizing our neural network, but still a long way from getting desirable results. When we write our code for neural networks, we will specify the number of iterations that we want this process to go through, called epochs. Because there were only 4 observations in the previous example, the process of backpropagation that we did for the XOR example would take very little time to fully compute. However, if you have thousands of variables and thousands of training samples, this process, in its theoretical form, takes a long time. Because of this, techniques to speed up the training while still obtaining reasonable results were developed. Instead of using all rows in the dataset in every iteration of training, the rows are randomly shuffled, and then a subset or mini-batch is selected to determine the change in weights needed for that iteration. As the modeling process moves on to subsequent iterations of training, the next randomly selected mini-batch is used, and so on. One epoch of training will now take on several iterations of this process, such that each mini-batch produced in this randomization process is analyzed in every epoch. As part of our coding process, we may specify the size of the batches that we want to use. If we choose a batch size that's too small, then the training of our network may take a long time. If we select batches that are too big, then our training may be inaccurate. Batches of size 32 tend to be a happy medium to mitigate both of these issues. The official name for this optimization method is called stochastic gradient descent, or SGD. There are several additional optimizers in the Keras package in Python that utilize the principles of stochastic gradient descent, but take their own methodology to help at finding the best set of weights and biases for our model. You can see a list of a few of them on the screen. You can also visit the Keras documentation pages to find more optimizers that might be used. Finally, a discussion about activation functions. In the previous week, we saw that in many cases, the direct output from a regular regression model will not take on a form that is appropriate for the data we're trying to predict. Because of this, we often apply an activation function to transform our data. For example, when we desired output values that fell between 0 and 1, such as the probability, we applied the sigmoid or logit function to our linear model. A similar form would be to use the hyperbolic tangent function. This is used when we want to get output that's between -1 and 1. We also saw the ReLU function when we worked with the XOR. In this case, the output should be 0 if the input was negative, and equal to the input otherwise. Another useful activation function is the binary step, where the output is 0 until we reach a threshold, and 1 once the input surpasses that threshold. In the graphic on the screen, our step occurs when the input is 0, but really this could happen at any threshold value. There are other activation functions beyond these, but these are ones that are very commonly used. One thing to note about activation functions is that it's important that these functions are differentiable or differentiable at all but one point, as we see with the ReLU and binary step. Why is that important? Gradient descent. The behind-the-scenes calculus in the gradient descent process utilizes partial derivatives of our linear functions as well as our activation functions. If these aren't differentiable, then the whole process breaks down.